Hello, good morning. So today we're gonna go through the rest of ideal gases. We've actually finished the content of the chapter already, so we just have to go through some of the questions. Okay, yeah, let's get started. Right, just move that here. If the music is a bit too loud, just let me know. Okay, so a bit too loud. Okay. Is that better? Okay, so what do we know so far? We know that PV equals nRT. This is the equation of state of an ideal gas. Oh, still a bit too loud. Okay. Drop that down to that. And then the other equation that we know is PV equals to nKT, where K is your Boltzmann constant. And we also have E equals to 1/3 rho V squared, where V here is the mean squared speed. What else do we have? We also have average, oh not average, sorry. Mean translational kinetic energy is equals to 3/2 kBT. Yep. So these are the 4 equations that we have to use in this chapter. Okay. Let's look at question 1. You have 2 gas cylinders A and B connected by some tube of negligible volume, as shown here. Each cylinder has a given volume. Hang on, let me make my pointer bigger. Let's see if these volumes. Initially, the tab is closed and the cylinder A contains some given mole of ideal gas and some temperature that's given. And B, you have this pressure and some temperature. Okay, so they both have the same temperature, but the A has 1.2 moles and B has this much pressure. Calculate the amount in mole of the gas in cylinder B. So they want you to find the number of moles here. So what do? You just use the ideal gas equation with number of moles in it. Alright. So that's just going to be PV equals nRT. Make n the subject. P is given. V is Gas constant is 8.31. Temperature is also given, but remember, temperature here must be the absolute temperature, which means it is in kelvins. Okay, put that into your calculator. And that's going to give you 0.93164 moles. Or you can leave it as 3 significant figures, which is 932, sorry. Okay, moving on. Oh, this is a bit distracting. Sorry about that. Okay, let's get rid of that. Let's just have no music up at all then. Okay, let's look at B. The tap is open and some gas flows from A to B. Using the fact that the total amount of gas is constant, determine the final pressure of gas in the cylinders. Okay, so you open the tube and some gas flows from A to B. Okay. And they're telling you that the total amount of gas is constant, which means your number of moles, the total number of moles should be the same. That means the total number of moles should be this guy plus this guy. Right, and they want you to find the final pressure. Okay, so again, we just use the same equation. Final pressure is P. So N is going to be the sum of the moles of the gases. So that's 1.2 plus 0.932. R is 8.31. Temperature is going to be the same temperature. So if the temperatures are different, you have to do something else, but we're gonna talk about that in in 2 chapters from this chapter. We talk about that in thermal properties of matter. So don't worry about that for now. For now, we can pretty much assume that the temperatures are the same when you have 2 gases and they mix together. And then V here is going to be the volume. The total volume is going to be 2 times of this guy. So that means it's 2 times of 2 times 10 to the minus 2. Okay, that's it. So put that into your calculator. One, two, three, four, 5. So that's 1.37 times 10 to the power of 5. There we go. We're done. Okay, that's it. Moving on. The mean kinetic energy is given as 3/2 kT. Estimate the temperature at the Earth's surface such that helium atoms of mass 6.6 times 10 to the power 27 could escape to infinity. You may assume that helium gas behaves as an ideal gas and the radius is given. Okay, so what do they mean by estimate temperature blah 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 such that the helium atoms could escape to infinity? Escape to infinity means it has escape velocity. Remember we did escape velocity back in chapter 2? So what is escape velocity? It is the speed required for a body to completely escape the gravitational influence of a planet. So it travels all the way to infinity. right? So what's the equation for that again? Uh, Actually, I don't quite remember as well. So let's try to derive it from scratch. You have to use change in EP equals to negative change in EK. EP is final minus initial, so EP is U is negative GMM over R. So we have negative GMM over RF minus minus, so plus GMM over RI equals to final is going to be 0 minus half mv squared. There we go. RF is going to be infinity, so this thing disappears. And this Ri is actually just the radius of the Earth. So in fact, we are left with half mu squared and then gmm over r on the side. Small m's cancel, making u the subject. We get our escape velocity, which is 2gm over r and then square root. So that's the escape velocity. Okay. So given that the mean translational kinetic energy is 3 over 2 kT, and kinetic energy is half mv squared, and then we can take this, substitute that in here. And then we can find T, which is the surface temperature of the Earth, right? So cancel that, cancel that. There we go. So m is going to be the mass of the Earth, which is the mass of the Earth is not given. That's strange. How are we supposed to find the temperature then if the mass is not given? That's weird. Hang on, let me just check something. Oh, I see. Okay, I get it. Hey, Modus, hello. It's not a carpet. It's a yoga mat. Okay, so in order to not use the mass of the Earth, you can actually use the gravitational acceleration. So that's gm over r squared. Okay, you can just use this, which means this guy here. Why do you sound so surprised, Modus? So this guy here is actually gr times m. Aha, there we go. The yoga mat is not just for yoga, Modus. You can use it as a regular mat. Downward dog. What's that? Is that like a yoga stance? Yeah, I don't actually do yoga. Sorry to disappoint you guys. I just use it to have like a soft surface when I'm, exercising. Okay. R is the radius of the Earth, which is 6.4 10 about 6. M is the mass of the molecule. uh, don't get any ideas, guys. It's not what you think it is. Times 6.6 times 10 to the power negative 27. So we have... Wait a minute, I think I messed up something because I got some weird answers here. Hang on a sec, let me just check. Helium atoms with this mass. If this is r squared, g times r. Yes, I think this is correct. Oh my god, what is... Oh, wait. What? No, it's not for VR. It's I use it for Ring Fit Adventures for the Switch. The K is missing. Oh yeah. Thanks for pointing that out. Forgot about the K. 1 over K. Okay, what is the K? K is a Boltzmann constant. Boltzmann constant is 1.38 times 10 to the power negative 23. There we go. 1.38 times 10 to the power negative 23. Okay, that's more like it. Otherwise, you get a nonsensical answer. So you should end up with 2.0 times 10 to the power of 4 kelvins. 20,000 kelvins. Want to do that phase, Modus? Okay, so you can see for the surface of the sun, it's about 5,700. So if the Earth's temperature goes up to 4 times the surface temperature of the sun, then the atmosphere is going to evaporate. It flies off to infinity. Poof. Okay, this I see. It is a pretty fun little game. Suggests why some helium atoms will escape the influence of Earth's gravitational field at temperatures below that calculated in this. Okay, so despite the fact that the surface temperature of the Earth is way below this amount, why is it that some helium atoms would still escape the influence of Earth's gravitational field? Why do you think that is? I'll give you a hint. The hint has to do with this. I'll give you a bigger hint. Okay, the reason is because this actually tells you the mean kinetic energy, not the kinetic energy of every single molecule of helium atoms, of helium, sorry, of helium. So, most of the helium atoms have this kinetic energy, but there are some which are much faster and some which are much slower. Exactly, the K is the average. So, some helium atoms have a much higher kinetic energy than the average kinetic energy. There you go, done. This is the standard answer, by the way. This chapter is so fun. Oh, really? That's good to know. I've always thought the second chapter is the one that's the most fun. I'm glad you enjoyed this one as well. Okay, and an amount of 1 mole of helium gas is contained in a cylinder at the pressure of this. Temperature is given. Find the volume of the gas. Not too hard and easy to understand. So that's your definition of fun. As long as it's easy to understand, it's fun. Okay, fair enough. So you're going to use PV equals to nRT, and you make V the subject. N is 1 mole, right? R is 8.31, T is 27 plus 273. 27 is the temperature that people use for the room temperature for chemistry. P is going to be 1.02 times 10 to the power of 5. Okay, what do we have? +273 divided by 1.02 times 10 to the power of 5. So we end up with 0.0244 meters cubed. There we go. Done. Next, show that the average separation of gas atoms in a cylinder is approximately this. Okay, so sometimes in the past years, they will ask you for the average separation of gas atoms. So what does that mean and how do you actually go about doing it? What's this? So what you want to do, there are 2 ways of doing this actually. You can model the gas atoms as spheres, or you could model them as cubes. So generally in the mark scheme, they model it as cubes. So imagine that, you know, kind of look like that. So each of these little dots represent a gas atom. Okay, so the average separation is going to be this guy here, X. Okay, so what is the volume? The volume is 0.0244. So if the volume is 0.244, in order to find X, or you could say X cubed is 0.244, which means X must be the cube root of that. Wait, why do I get something weird? That's not what I'm supposed to get. Okay, this is correct. Oh, 0.244. Okay. Let me just double check. Wait, what? I got 0.0244 though. So this is correct. Oh, this thing. Okay. Okay. I see what you mean. It's this one that I messed up. Okay, so cube root of that. Cube root of 0.0244. 0.29. That is also not what I'm expecting to get. That's strange. Is it the number of particles in this? Oh yeah, you're right. I completely forgot about that. You are absolutely right. 1007 sun. Because the this volume actually represents the total volume of the gas, not the volume between 1, 2, 3, 4, 5, 6, 7, 8 particles. So let's work out the number of particles first. So number of particles is 1 mole. Okay, we have 1 mole of gas. So what you got to do is take the volume and divide that by the number of moles. So we have volume divided by the number of moles, or number of particles, sorry, which is 0.0244 divided by 6.02 times 10 to the power of 23. So we're going to do that first. Which is 4.05 times 10 to the power of negative 26. Okay, so once you've gotten this is actually the volume occupied the average volume occupied by one single particle of the gas. So if you model it as a cube, that means it kind of looks like a, how should I draw this? Kind of looks like this. So it is the volume occupied by this guy right here. So you can still use the fact that x cubed is equals to 4.05 times 10 to the power minus 26, because this guy here is going to be, half x, and that guy here is half x as well. So they would add up to give you x, which happens to be the separation between two particles. So doing that, we get cube root of that, which is 3.44 times 10 to the power negative 9. And there you go, done. Alternatively, you can model it as a sphere, which means you would do something like each particle occupies like a sphere. So the average separation between two spheres, so this would be 2r essentially. So you could do 4/3 pi r cubed equals to this guy. You're not going to get the same answer though as this one, because you're modeling it as a sphere. But the mark scheme, usually they would accept both. But for this particular case, they only accept the cube, because only the cube would give you this answer, I think. Anyway, let me just work this out first. Then we cube root that. So r is going to be 2.13 times 10 to the power of negative 9. So 2r, which is going to be the separation, is 4.26. So there you go. As you can see, it's very similar, but not quite the same. So if they didn't specify a specific number, you can use either this one or this one. It's up to you. You get an answer that is acceptable by the mark scheme, that is accepted by the mark scheme. Okay, there we go, done. Explain qualitatively how molecular movement causes pressure exerted by a gas. Okay, so according to the ideal gas assumptions, the collisions with the ideal gas molecules with the walls of the container is perfectly elastic. And because it collides, and there's a number of particles which collide, whenever you collide with something, there is a change in momentum, right? And if you have a change in momentum, you have a force. And if you have force, you would have pressure. So that's how molecular movement causes pressure in a gas. So the way you want to explain this is by writing these three things. Molecules rebound from walls of the container, causing a change in the momentum, resulting in a force, and the average force due to the random motion results in pressure. So you can just write that down. This is the standard way of answering questions like these. Okay. Alrighty, let's continue. The density of neon gas at some given temperature and some pressure is this one. Neon gas is assumed to be an ideal gas. Calculate the root mean square speed of neon gas. Okay, how do you find the root mean square speed? So we know what the mean square speed is. The mean square speed looks like that. The root mean square speed is essentially the square root of this, which gives you just this. Sometimes it's referred to as the RMS speed. Okay, so how do I find the RMS speed? Well, we know that the kinetic energy, but actually no, what am I saying? All you have to do is use the equation P equals to 1 over 3 density times this guy squared. The reason you want to use this equation is because the density is given. So that's usually a hint that you should use this equation. So let's make this guy the subject. So we have 3p over rho and then square root. Okay, so P is going to be 1.02 times 10 to the power of 5. Rho is 0.900. So putting that into your calculator, we get 583 meters per second, almost 2 times the speed of sound. Okay, next up, what if the temperature is 546 kelvins? Well, you might be saying, oh, wait a minute, this one doesn't seem to have temperature in it, so shouldn't it just be, the same? No, because this values here and these values, they are only for neon gas at this specific temperature. I don't even that many kelvins in the world. You might be surprised. Hello, X Decent. Hello, hello. So, the other thing that you want to recall when it comes to the temperature of an ideal gas is that the temperature is only proportional to the average or the mean translational kinetic energy of the gas. Okay? So, remember there's this equation, T is equals to, hang on, no, not this one. Hang on, let me just fix this. No, X decent, Gaji hyper. So 3 over 2 kBT. There, this guy. Remember this guy? So you have to use this equation. And this guy here is half mv squared. So if your v is doubled, let me just rearrange this so you can see what's going on. So we have 3 times k over m times t. So you can see this guy here is actually just a constant, which means this guy is proportional to t. And then what that tells you is that initially when your t is 273, your v was 583 squared, right? So you can imagine this is just some constant. This guy is equals to some constant times t. So now we have 546. The constant should be the same, and now you're trying to find v squared. Okay, so this is equation 1, equation 2. So you could just say equation 2 divided by equation 1 to get rid of the k. Haha. So that's going to give you, what is 546 divided by 273? 2. So you get 2 equals to this divided by this, which means this guy is in fact 824. Hey, done. So that's the shortcut to finding the new speed, just by using the ratio. Okay. The flash. Bungo tap. That emote is so cute. The longer way of doing this is by using this equation again. Or you could use, what was it? Yeah, you could use some of the other equations to find all these other values, but no one has the time for that. It's much easier if you just use the ratio. Okay, that's it. We're done. The calculations are based on the density being this guy, suggest the effect, if any, on the root mean square speed of changing the density on the temperature, at constant temperature, sorry. So what happens if you change the density but you fix the temperature? What happens to your root mean square speed, which is this guy here? What do you guys think? Changing the density but maintaining the temperature. What's going to happen to the root mean square speed? Such constants. The answer is nothing happens, because for an ideal gas, the temperature is only proportional, or I should say, temperature only depends on the average translational kinetic energy. So changing density doesn't affect the root mean square speed. Okay, they always ask you something like this in the exam. They might not necessarily refer to the density. They might say, oh, what if I change this variable? But as long as the variable has nothing to do with temperature, the root mean square speed always remains the same. So there you go. Now let's look at the next question. I think this is the last question. Yep, the last question. An ideal gas occupies a container of this at some pressure and some temperature. Show that the number of atoms in the gas is given to be this guy. Okay, so now you want to find the number of atoms, not the number of moles. So you have to use this equation, PV equals to capital N KT. So N is going to be PV over KT. P is given. V is this guy here. K is the Boltzmann constant. T is the absolute temperature, which is 290. And you put that into the calculator. And you get 2.36 times 10 to the power of 34. There we go. And then next up we have atoms of a real gas have diameter of this. Estimate the volume occupied by these many atoms of this gas. Okay, so again, you can model it as a sphere or a cube. It's up to you. Let's say we model it as a cube, right? So, oh, but this is a diameter though. They mentioned diameter. So if they mention diameter, I think they want you to model it as a sphere, because cubes don't have diameters, right? So, let's see. You have the volume of a gas is 4 over 3 pi d over 2 cubed. Putting that into the calculator. That's going to give you 0.6 times 10 to the power negative 10 cubed, which is going to be 9.05 times 10 to the power negative 31. So this is the volume occupied by one particle of the gas. And then the total volume occupied would be the volume times the number of atoms of the gas, which is going to be 2.53 times 10 to the power negative 7 meters cubed. And there we go. All right, so now that we have estimated the volume occupied by this gas, by reference to your answer, suggest whether the real gas does approximate to an ideal gas. Okay, so so you can see here for an ideal gas, the volume of the container is 4.5 times 10 to the power 3, right? But then the volume that the gas occupies is only 2.53 times 10 to the power negative 7. So that is a lot bigger, a factor of 10 actually. So it is like 10 with 9 trailing zeros behind it. It's like, what is it? 10 million times bigger. So yes, it does approximate to an ideal gas. So yes, it does, because the volume of the gas is much smaller or negligible compared to the volume of the ideal gas. There. Okay. So whenever they say whether something approximates to an ideal gas, you have to make some kind of reference to the ideal gas assumptions. So remember, one of the assumptions of the ideal gas is that the volume of the gas is negligible compared to the volume of the container. So that's the one that you want to use. Okay, that's it. We are done with the questions. So for now, you should be able to do the rest of the questions on the past year paper. Okay, topical past years, you can attempt that. And yeah, we're done with this chapter. Quite a short chapter, actually. Right, so do you guys want to start a new chapter? We can actually do temperature next. It's a fairly short chapter. Yeah, actually, why not? We could do a new chapter. So let's take a 5-minute break, and then I'll see you guys in a bit. Okay, let's start with the new chapter then. So I've uploaded the notes and stuff onto Google Classroom, so you could download it from there if you haven't done so already. So the next chapter is actually a really short chapter. We can probably finish it today. So previously in the last chapter, we've learned that the temperature of an ideal gas depends only on the mean kinetic energy, right? So how exactly do you measure temperature? How do you calibrate the mercury in glass thermometer, and what are the different kinds of thermometers are there? So the definition of temperature is going to be the average kinetic energy of particles. Kinetic energy here would include things like translational kinetic energy, vibrational kinetic energy, rotational kinetic energy, depending on the configuration of the particles. For ideal gases, you only have translational. For things that are molecules, you might have rotational energy. Solids, you have vibrational kinetic energy, but you don't really have to know those things, those different modes of kinetic energy, because that's not in the syllabus. You can just ignore that. Yeah. So, hex. So there you go. Next up, we have heat, which is the phenomenon where you transfer energy from a hotter body to a colder body. So, a common misconception that people have when you are talking about temperature is that people say if something is hotter, that means it has a high temperature. If something is colder, that means it has a low temperature. But that is not exactly true, because what you actually mean is that if something is hotter, that means it has a higher temperature relative to your temperature. For example, you can do this experiment very easily at home. You get 2 cups of water. 1 cup is, let's say, you can put half boiling water, half normal water, so it's warm water. And the other one, you can put it in the fridge, right? And then you take them out. And then you take another cup of water, let's say a lukewarm room temperature cup of water, put it in the middle. So something like this is room temperature water. This one is hot water. And then this one is cold water that you have taken out from the fridge. Yes, lukewarm water. What's with that face? So what you want to do is you take your hands, right? Because initially your hands they are room temperature, and then you put them one in hot water, one in cold water, and you just leave it there for a while to let the temperature of your hand be the same as the temperature of the hot and cold water respectively. And then you take them out, and then you put them in the middle, the room temperature water. So what you're going to feel is that the hand that was previously in the hot water would feel cold, because the room temperature water is colder compared to the hot water. But then if you put your right hand from the cold water into the room temperature water, it feels warm, because it is warmer than the cold water relatively. So using your sense of whether something is hot or cold is not a very good way to measure the temperature of a body, because the only thing you can tell is whether it is hotter or colder than what you are currently perceiving. You can only perceive the relative difference in temperature, not the actual temperature itself. You can't say, I'm gonna put my hand in there. Oh, this is 34 degrees. It's impossible. You can't do that, right? So what do? That's why you need a thermometer. Okay, so next up we're going to talk about thermal equilibrium. So the thermal equilibrium is what happens when you put two bodies in close contact with one another. So when you put two bodies in close contact with one another, let's say a warmer body and a colder body, you put them together, there's going to be some heat transfer from the hot body to the cold body. And eventually you get to a point where the heat transfer becomes zero, and that's when the temperature of the bodies become the same. So that is the driving principle behind thermometers. Okay, and well, basically whenever you put two bodies with different temperatures next to each other, eventually at some point they would have the same temperature because of the laws of entropy. You don't have to worry about what entropy is. It's not in your syllabus. Okay, so next up, let's talk about how to calibrate the mercury in glass thermometers. XDson is so excited. Nani? So, let's say you have a glass container and you put some mercury in it. So mercury is very sensitive to changes in temperature. That's why we use mercury. I mean, aside from, the fact that mercury doesn't quite evaporate as easily, and the fact that it is very sensitive to changes in the temperature. So a slight change in the temperature changes the volume of mercury. So you use mercury in a glass container, like most regular thermometers that you see in the labs. Okay, so how do you calibrate that thermometer then? The first thing you do is you put that thermometer in pure ice. Pure ice is just pure water that's, frozen. And you just put your thermometer in there. And then your mercury is going to be at a certain level. So what you do is you mark that level, and then you label that as 0 degrees Celsius. Okay? And then you put that into boiling water, and that mercury is going to rise to some temperature up here, and then we're gonna mark that level, and then we're gonna label it 100 degrees Celsius. So now that we have two of these things marked, we can actually just divide this line here by 100, and then you mark at equal divisions. And that's how you calibrate a thermometer. So this is, a mercury in glass thermometer is only 100% accurate at these 2 points, 0 degrees Celsius and 100 degrees Celsius. The rest is actually just conjecture because you are dividing this length by 100. And if you do that, you are actually making the assumption that the increase in length of the mercury is linearly proportional to the temperature increase. But that may not be the case. In fact, there's usually a small slight deviation. It may not be completely linear, it might be slightly curved. So it could be something like, let's say this is the temperature, this is the length, and then this is, let's say, 0 degrees Celsius here and 100 degrees Celsius here. What you think is actually happening is like this. This is what you expect. And then what actually is happening, happening. Could be something like a slight curve, like that. So here and here, 100. And this kind of reminds me of the what you expect and what is actually happening meme. But yeah, anyway, it kind of looks like this. So the ones in the middle might not be entirely accurate. So just bear that in mind. Okay. Anyway, moving on, we have the thermistor. So the thermistor is some variant of the thermometer that uses the resistance as a measuring parameter. So for the mercury and glass thermometer, we use the length of the mercury as a measuring parameter. Oh, well, they call it the sensing parameter, I think. But for a thermistor, we use resistance as the sensing parameter. So, however, resistance is inversely proportional to temperature. And it actually looks like a 1 over x graph, kind of look like this. Okay. So, you should have your notes with you right here. Thermometers. So, under thermistors, you can write the advantages and disadvantages of the thermistor. You want to write these guys here. So the thermistor has a small thermal capacity. We'll talk about thermal capacity in the next chapter. So all you're gonna know for now is that it is sensitive to small changes in temperature. The measured temperature deviates less from the actual value because it is quite linear, even though it doesn't look very linear, but it is actually fairly linear. And the sensing circuit is simple. The disadvantage, it is mostly non-linear, and it has a narrow range. You only use thermistors if you want to measure small changes in temperature, but not like gigantic range. It's only for like a small range. There. So I'll just leave it here for a bit so you can write it down. Unfortunately, you're gonna have to memorize this because they like to ask this in the exam, the advantages and disadvantages. It's 3 marks, so just commit them to memory and just vomit them out in the exam. Easy marks. Yes, just vomit it out. Projectile vomit. Ugh. Okay, you guys done? Moving on. Next up, we have thermocouples. So, a thermocouple is a thermometer that works by using the potential difference as a sensing parameter. And the driving principle behind a thermocouple is the Seebeck effect. You don't have to know what the Seebeck effect is. They are not going to ask you what the Seebeck effect is. But essentially what the Seebeck effect does is if you have a piece of metal and you heat up one end of the metal, the electrons on that end of the metal is going to flow to the cooler side of the metal. And whenever you have a flow of electrons, you have a current, right? So there you go, which means one side would have a slightly more positive potential compared to the other side. So if you have multiple wires which have, different metals, let's say you have these 2 wires, and then this wire is made of a different material, and you hit this end of the wire, the Seebeck effect is going to cause these 2 wires to have a different current, which means you're going to end up with a potential difference between these 2 junctions. And that's going to be measured by this V over here. This is actually a very simplified look of the circuit. The actual circuit is actually way more complicated than this, but I've just drawn a very simplified diagram of the actual circuit. So you don't have to know how the circuit works. They're not going to ask you to draw the diagram of the circuit. They're just going to ask you about the advantages and disadvantages of the thermocouple. So that's pretty much all you have to know. So the advantage is it has a very wide range, rapid response, mostly linear. You don't need a power supply. You just have to get two ends of the thermocouple. We put one end in a control, the other end into like whatever you're trying to measure, and then that's it. The disadvantage is the sensing circuit is complex and is susceptible to noise. The thermocouple is able to measure up to thousands of Celsius. So if you want to measure something extremely hot, you want to use a thermocouple, not a thermometer like a regular mercury in glass thermometer, because that would probably melt. So there you go. If you want to measure extreme temperatures, use a thermocouple. So I'll leave it here so you can write it down. Okay. Right. So, yeah, we're pretty much done with the theory part of this chapter. So for the questions, we're going to go through that in the next class. There's actually not that many actually. So I think next class we'll go through all the questions and then we'll get started with thermal properties of matter. Yep. Can it measure temperature of materials that don't conduct electricity? Yes, you don't need you don't need the material to conduct electricity. So usually what happens is you have the object that you want to measure. So this is the body that you want to measure that needs to be measured. And then you have your thermocouple device with usually two ends. So one end would you sort of touch this body, and then the other end you would touch like a control. So this is like a control. And then you get the temperature reading on the thermocouple itself. The conduction of electricity only happens in the thermocouple itself. So this diagram represents the thermocouple itself. The junction, you just have to put it in contact with whatever you are trying to measure. And that's it. That's all that you have to do. It doesn't matter if the body is an insulator. As long as it is in contact with the thermocouple, the Seebeck effect is going to happen, and then you get a measurement. Yep. Okay, that's it for today. So, over the weekend, you can try doing some of the ideal gas past year questions. You can try that. And if you have anything, we can discuss next class. Otherwise, we'll continue with the questions and then we will start the next chapter. So I'll try to finish as much as I can before I leave you guys forever. Because, as you know, this is my last term. Next term, we will have someone else taking over. Yep. Anyway, see you guys. Bye-bye. I'll see you next week. Laters. Bye-bye.